company does atomically precise engineering of diamond qubits to provide a leading qubit platform for mass-deployable quantum technologies across computing, sensing, and communications. So please join me in welcoming Dr. Doherty. Hey, how are you, man?
So good afternoon, ladies and gentlemen. So as Chris graciously invited me to come up and introduce my talk, what I'll be addressing today is firstly that diamond is the proven and to a great deal solid in a generalisation that it is the choice platform for mass deployable quantum technologies. And the reason why that is the case is because diamond qubits have incredibly long coherence times, incredibly high quality in terms of their fidelity, and they operate entirely at room temperature and in ambient pressures. And they can be miniaturised with control systems which are compatible for deployment out into the real world rather than in laboratories or specifically designed environments. And that is really offering an alternate version of the future of quantum technology, one that complements the technologies being developed elsewhere, such as trapped ions and superconductors and these sorts of things, where it complements those technologies being confined to, say, supercomputing centres, with diamond-based quantum accelerators being deployed out into the real world in a distributed sense and out to the edge in the computing network. So what I'll talk about today is I'll firstly introduce who Quantum Brilliance is and what we are doing. Then I'll talk more broadly about diamond quantum technologies, and I'll lead you to the key point that the main blocker that diamond quantum technologies has faced to date has been the ability to precisely engineer the qubits. And that with the advances that we have made in Quantum Brilliance and our new ventures in developing a foundry business, we will unlock that burgeoning potential for mass deployable diamond quantum technologies across the three different technology verticals of sensing, computing, and communications. So I'll begin with the introduction to who Quantum Brilliance is. So our end vision, the thing that drives us every time we come to work, is the realisation of a quantum accelerator. That is a quantum computer which is the same size, weight and power as today's CPUs and GPUs. That they will be integrated wherever classical computers are today. So they will be in autonomous vehicles, in satellites, they will be in workstations in your laboratory or your place of work, they will be with CT scans in hospitals, they will also be massively paralysed in high-performance computing centres and data centres alongside the future of what we call quantum mainframes, such as superconducting quantum computers, trapped ions, etc. The key to realising this technology is on the left-hand side, which is the integrated quantum chip, which is at its core a piece of diamond that has precisely placed nitrogen vacancy centres, which Rene graciously introduced in the previous talk. And they are placed with precision of sub-nanometre and they're spaced on a 5-nanometre scale. That precision then enables all of this else, which means that we can scale up the computational power. The inherent properties of diamond mean that these qubits operate at room temperature, and the control electronics, there's a clear pathway to already shrink that down to that CPU, GPU size. So the key thing to solve here is the ability to fabricate these qubits. And I was talking about here before is that this is the full spectrum of applications. It offers a great more diversity of the way to deploy quantum computing than other systems have and constrained to very particular ways to deploy quantum computing, such as in centralised computing. Another founding thesis of who Quantum Brilliance is one where to deliver commercial value, so when a person will actually choose to buy a quantum computer compared to a classical computer, you've got two dimensions to play with. You can keep your quantum computer large, and you can add more qubits and increase its fidelity to the point where it outperforms a supercomputer, a classical computer of comparable size, weight and power. So at that point, the architects of the supercomputing centres around the world will go, yes, it makes sense for me now to buy a quantum computer because I can see how I can integrate and fit that and use that. Another way to commercial value or delivering a choice where people go, yes, I want to buy a quantum computer, is instead to shrink down your quantum computer so that now outperforms individual CPUs and GPUs. So when a consumer or whether a person who's trying to engineer an edge computing system says, what's the best computer for my application, they have constraints around size, weight and power, and they choose the quantum accelerator over the classical accelerator that meets those constraints. And so that idea of the importance of shrinking down size, weight and power and what that means against what classical computing system you're compared against is one of the central theses of what we do at Quantum Brilliance. So we founded the company in 2019, and over the last 5 years, we've built a company which has 3 key business units and capabilities. One is in the extreme engineering of diamond to produce quantum diamond. Another one is in the fabrication and design and development of integrated quantum devices. And the last one is about the construction of computing systems and the software that enables you to actually run massively parallelized as well as edge computing systems and the flagship applications that drives the value in those alternate ways of deploying quantum computing. And so we're approximately 80 people, half of them being in Australia and the other half being in Germany. And so in Australia, we are stablemates with other world-leading quantum computing companies such as Q-Control, which you heard from Mike earlier today, as well as Dirac. And we build on a very long history of excellence in diamond quantum technologies in Germany. So one thing that we're proud of, and I haven't heard anyone argue with our claim yet, is that we were the first company to actually deploy a quantum computer into a supercomputing centre, fully integrate that quantum computer into the supercomputer and run hybrid quantum algorithms directly in that supercomputing centre. And so this is the work that we did with our first customer being the Pawsey Supercomputing Centre in Australia. I spoke earlier about not only do we develop the hardware, but we also develop the software for this alternate approach to quantum computing, being mass parallelization, as well as deeply hybrid computing that's deployed to the edge. So we've developed a software development kit called Crystal that enables people to actually orchestrate those different computing systems and to be able to emulate the performance of those computing systems now and also into the future with larger number of qubits. And we've done that in conjunction with NVIDIA and Oak Ridge, who have from a very early days shared the vision with us that the future of computing will be one which is deeply heterogeneous with different types of computing and one of mass parallelization. So where we are today is we have our desktop-sized quantum computer on the far left-hand side. What we are going to be deploying to a national laboratory in the US this year is the first cluster of quantum computers which are managed by a special server that manages that computing cluster. What we'll be doing in the next 2 years is then demonstrating field-deployed edge quantum computing, and then at 2029, that first product line that we believe will outcompete individual CPUs and thus present a real choice to consumers about do they buy a quantum computer or do they buy a classical computer. So bringing it back to the main topic, which is about the precision engineering of qubits and diamonds. So at the heart of realising that vision is the creation of an integrated quantum chip. In the middle of that is a diamond containing that precise array of qubits I talked about earlier, but that is then integrated with photonics layers, nanoelectronic and microelectronic layers, and then finally magnetic layers to create a semiconductor stack, which is packaged up as a chip, which in the end will be a very boring looking black chip, just like every other processor that you see on an electronics board. So what about other diamond quantum technologies? So what are they doing, and how is our work related to what they are doing, and how can we go faster together? So I've talked about diamond and why it's special. I won't go through this one anymore. What I will talk about is what's happening commercially. There is a very large number of very large players who have now developed who are now developing diamond-based quantum sensors, computers, and also communication systems. So those that I've got there on the left-hand side on the diamond-based quantum sensors, that's one of 50 plus companies who are developing diamond-based quantum sensors. And they include very large companies such as Lockheed Martin, Thales, as well as Bosch, who have all created prototype devices and are now looking at how do I actually turn this into a product from a prototype. You obviously have us in the middle with quantum computing, and then you have AWS, who's placed a bet on Diamond as being the platform for the future quantum internet. And so they have now created a substantial team within AWS building quantum networks based upon Diamond qubits. So to give you some tangible examples, we've heard earlier from previous speakers around magnetic positioning. So this is the idea of using ultra-precise magnetometers to position you relative to a magnetic map. So Lockheed Martin demonstrated this 5 years ago with their dark ice diamond-based quantum sensor, and they've further developed this technology. But that's only one of many quantum sensing applications of diamond. And so if you look down the bottom, this gives the full spectrum of what I would call macro sensing. So this is detecting radio waves, or detecting the Earth's magnetic field, or detecting macroscopic amounts of chemicals. And if you think about micro, then because these qubits are atomically sized, you can also use them to perform microsensing and microimaging. And this spans things like fundamentally new technologies to actually image semiconductor devices which are coming off the production line. And so we have companies like Qnami and QCAT who are developing semiconductor inspection tools based upon diamond quantum microscopes. And so this is real industrial activity with real people purchasing these things in order to use them for real applications. That's the example of the pre-production prototype that Bosch has for a diamond-based quantum magnetometer. The use cases they have in mind for that is in monitoring batteries in electric vehicles via the magnetic emissions of those batteries. And on the right-hand side, that gives you an idea of where AWS is currently at in prototyping their photonics-based quantum networks using qubits and diamond as the key qubit in that network. Now, when we talk to Bosch and to others, the core challenge they have is the material does not yet meet the performance requirements, i.e. precision, and is not yet sufficiently manufacturable in order to really bring these products to market. And so we are in the process of translating the engineering that we have done to create quantum computers into servicing those needs for quantum sensing. And so fundamentally, another way to state that problem is that diamond quantum sensors are on the left-hand side, which is that they really are prototypes of lumped elements of lasers and optics which have been screwed together. That limits their performance and limits their manufacturability. The key evolutionary step that diamond quantum sensors have to go on is to become an integrated quantum device. Just like what we need for our development of a quantum computer, they need for the development of their quantum sensor. And so where are we at then in all of this? We have, over the last 5 years, ticked off various key proof points about how to build that integrated quantum chip. So that's in parallel with building our early prototypes, which contain a few qubits, to do all of that work I talk about with supercomputing centres and these sorts of things. In parallel to solving the packaging and deployment integration problem, we have also been working on developing the heart of the quantum computer, which is the integrated quantum chip. And the things we have ticked off is how to go about fabricating that precise array of NV centres, and I'll show you some actual proof of that in a second. The next thing is, how do you actually read out and initialise those densely packed nitrogen vacancy centres in that array using a new process which is called photoelectrical detection, which exploits nanoelectrodes in order to interface with those NV centres. So there's another key step, which is that integration of quantum, being the NVs, with the nanoelectronics. And the last one is then, okay, Well, what is a key enabler for scaling up the number of qubits? And that's the production of microelectronics that allows you to produce field gradients to then individually address the different nitrogen vacancy centres in your array when you're performing quantum operations. I won't talk about the latter two. What I'll do is I'll focus on that first one, which is about the precise material engineering. So we employ a technique called atomic scale fabrication. This is a technique that was developed on silicon over 20 years. And what you will have seen is quite recent news about how this technique is now being transferred into mass manufacturing in silicon through the demonstration that extreme UV lithography can perform some of the key steps of this process. The innovation that we did at Quantum Brilliance was to translate this technique from silicon onto diamond. And so what the process involves is a very high precision preparation of your diamond substrate. So that is taking diamond substrates as received and processing them to make them very high quality, i.e. no defects, and also very high precision in their geometry, i.e. they have a very precise surface at a precise angle and they meet a range of geometry constraints, the same constraints that are required to enter into high precision lithography for scalable manufacturing of integrated devices. After this point, there is a step called hydrogen depassivation lithography, which is where you remove a patch of hydrogen from the surface of the diamond to expose a chemical reactive site from the carbons underneath. So once they've had their hydrogen removed, they now have dangling chemical active bonds, which will then seek to react with a substance. What we do is we introduce a nitrogen containing chemical, which reacts with those sites and not the rest of the diamond surface, includes the nitrogen into the surface, we overgrow to form the nitrogen vacancy centres, and we have our array. And a key thing about that overgrowth is the retention of the nitrogen, the conversion from nitrogen to NV centres, and the alignment. So that direction from the nitrogen to the vacancy in that NV centre are all pointing the same way across that array. So here are some results. So what you see in the top left-hand side is a scanning tunnelling microscope image of the diamond surface over a scale of 100 to 200 nanometres. And those stripes that you see are individual steps or terraces which are a single atom high. And so, the laser doesn't show up too well, but you can see from here to here, this is atomically flat, and then there's a step, one atom down to then another terrace, which is then atomically flat. That is the outcome of our precise substrate preparation and processing, is this extreme and controlled flatness of the diamond surface. The next thing we did is really learn about the diamond surface, how to image it and understand all of the defects which plague that diamond surface so we can correct them. So through the combination of experimental work, computational work, and the use of artificial intelligence, we created a library that can allow us to diagnose and correct the diamond surface. The last thing we did was we transferred that lithography technique, hydrogen depassivation lithography, from silicon to diamond. And so at the top, what you can see is a zoomed in image, which is the yellow bar there is 10 nanometres, and you can see the individual white dots are individual silicon atoms. On the right-hand side is then an image where we've removed the hydrogen, which creates a bright mark. So we removed individual hydrogen atoms on that silicon surface to create a diamond on the silicon surface. We've then done that again on diamond. And so on the bottom you can see a picture of the diamond surface where each of those blobs are individual hydrogen atoms on the diamond surface. On the right-hand side is our atomically precise lithography. So the red dots on the right-hand side is where we wanted to remove a hydrogen atom. The white dot is where we did remove a hydrogen atom. And the difference between those 2 points is 5 nanometres. So we do have some work to go yet to improve the accuracy and the precision of our technique, but it gives you a sense of the degree of control that we have over this lithography process. The second thing is, okay, you've been able to create this lithography. can you actually terminate that surface with nitrogen to introduce the nitrogen, and can you overgrow to then create that NV layer? And so what we have here are results where we have a diamond, we have nitrogenated the surface using our chemical, we've then overgrown. There are a couple of key outcomes. Firstly, we achieved nearly 100% retention of the nitrogen. That all that nitrogen we put down, almost all of that nitrogen retained when we performed the overgrowth. So that's really important to the yield of our qubits. The second thing is it stayed exactly where we placed it. And so if you look at the bottom, these red dots indicate that all of that nitrogen is found within a region that is less than 4 nanometers deep, which is the resolution that we could achieve using this technique to measure where the nitrogen was. So all of that nitrogen really is in that surface layer where we created it. On the right-hand side, this then shows that conversion from the nitrogen to the NV, so the formation of the qubits. That is a vertical scan of a confocal microscope. The bright line is those qubits in our diamond. At the bottom, what it does is it shows you what is the alignment of those NV centres. So the red shows you that there is only one species of NV centres, whereas the blue, which is a reference, a control, shows you the other alternate species. And so this says that we can indeed do all of those things, which is the precise lithography, the deposition and retention of nitrogen, the formation of the nitrogen vacancy centres, and the alignment. This is the technology that's required to create that step change in performance in diamond quantum devices, not only for our quantum computing technology, but for all those other companies who are building diamond-based quantum sensors. And so with that, I'll thank you, and I'll call it there.